I welcome you all in today's talk. And the intuition is that we would like to get some philosophical touch to understand in a philosophical way the meaning of perturbation. And I would like to start with an example. I have imagined a couple of small stories that I would like to share with you. And these stories will guide us to whisper, to understand the meaning of perturbation in physics. Now, to start with, if I imagine that there is a lake, at the dawn, there is a lake, and this lake is silent. There's no disturbance acting in the lake. And this lake is acting as a mirror to the sky. You can see the sky at the dawn. You can see the reflections of the sky in the lake. Now assume a pebble in your hand. A pebble in your hand, and you drop this pebble in this lake. Now what it does, it creates waves, it creates vibrations. And there is symmetry in those vibrations. So what you are doing is you are disturbing the calmness of this lake. And if I think in terms of the ideal problems that we have solved in quantum mechanics, the problem of a particle in a one-dimensional box, they are the lake that I described you. But when you disturb this lake, that too over a period of time, that disturbance causes the change. Even though that change is extremely small, for a short note of time, this reflects perturbation, time-dependent perturbation. So you are able to sense the symmetry that evolves in that lake by virtue of that small disturbance that you are inserting in the lake. Now see, there is not anything like violence. You are not allowed to throw the stone in the lake. When you throw the stone in the lake, it becomes violent. And this violence leads to scattering. That's your fourth chapter. We are not violent here. We're very subtle. Let me take another example. Let us assume that I'm in a room and I carry a tuning fork. You have seen a tuning fork in the laboratory. We have a tuning fork when you perform that experiment of sonometer. And in this room, there is a violin. You understand violin? It has strings, it has wires. Now, if I disturb the tuning fork here, it will vibrate. you may listen the vibrations from the violin. You're not touching the violin. The violin is in the room, but there is a possibility that the vibrations that you're producing in the tuning fork, their frequencies may match the natural frequency of the wire of your violin. If the two frequencies match, your violin will vibrate. I'm getting my point? Without making any physical contact to the violin, the resonance makes it possible. The perturbation makes it possible. Because the disturbance that you have generated, it has a frequency. If it has a frequency, it has a dependence on time. This disturbance has a changing nature in the background of time. That's what is called time dependent. And what is time independent? What's time independent? You are disturbing your system, but the disturbance that you are using is a constant. It does not depend on time. It remains same. It's not changing. So when your disturbance changes, you have a dependence of time. So in the background of your calculation, you have time. You have a mathematical equation. What you do now, you incorporate time in your equation. So when you incorporate time in your equation, you talk about the time-dependent perturbation. Now see, everything is not possible. I use a tuning fork in my room. Only certain vibrations are allowed that will match with the frequency of the violin. So in quantum mechanics, you have allowed transitions and you have forbidden transitions. It is not all the frequencies of the tuning fork that will match with the frequency of the violin. Only some selected. And giving birth to what's called as selection rule in quantum mechanics. You have allowed transitions and you have forbidden transitions. Now I want to quote down another example to understand the same thing that I'm trying to explain. Now let me assume that I'm in a ground and this ground is filled with fog. It's filled with haze. Okay? So when it's filled with haze, I can't see. I don't know my destination. I don't know where am I going. Imagine in that haze, there is a lantern. And a lantern lights somewhere in a haze. It just lights and closes. What will I do? I will follow the direction of that light spot that I saw. I saw it for a very short span of time. What was my identity before that shot of light? I was everywhere. I had no destination. But a small flick, a small click of light, it changed my course. I moved towards that light. So this is how quantum works. Sometimes new paths come in action. These paths don't exist. But these paths have an origination by virtue of that perturbation. Lighting up the lamp. I am in a haze. I am in a fog. I see a short flash of light. And I move in that direction. This is how time-dependent perturbation works. Getting my point? So what we have, we want to understand this. We want to have some more deep understanding. I think these examples, they certainly might have given you some idea that what actually we are doing in mathematical framework, what our intuition is basically. You have a disturbance, but that's a beautiful disturbance. That does not disturb the lake in a violent fashion. Your disturbance causes symmetrical wavelets in a lake of water. Your disturbance causes a person to know its destination when it is trapped in a fog. Your disturbance vibrates a violin which you have not even touched before. This disturbance is time-dependent disturbance. So we call this as time-dependent perturbation. All right? So again, I will go with the same thing because I want you to have a catch on it so you understand what perturbation is. It is a kind of disturbance that you disturb your system. That system is in a sleep. And you feel you know everything about this lake. It's a sleeping lake. We know it. We solve the Schrödinger's equation. Okay? So you gently disturb the system. We assume that we understand system already without the disturbances. We assume we understand. Then we tweak it slightly and see how it responds. So what is the nature here? Talking about the classical objects, talking about moon, talking about football, talking about planets. Certain, you're certain. You are completely certain in the classical domain. You have an object, you know the initial conditions, you can exactly predict. You are certain where the duster will fall, how much time this duster will take to reach the target. So in classical physics, you deal with certainties. You're certain about the outcomes. But here, you are dealing with probabilities. Your results are probabilistic. Now think about the person in a haze. How will I define this person moving in a fog? I'll say it has all probabilities. It can choose any path. Maybe it's everywhere in the system. So this is how quantum mechanics works. It does not work in the framework of certainties, it works in the framework of probabilities. You talk about the probability that there will be a transition of an electron from ground state to excited state. You don't say that it will. You simply say it has a probability to make this transition. And it has a probability not to make this transition. Both statements are true, right? So your quantum systems are defined by possibilities, probabilities. They live in a world of probabilities rather than that of certainties I was talking about. A state describes what a system is doing. Okay? We don't have the physicality of that state, the wave function, right? Or more precisely, what it might be doing when I will measure. These are the two important, these are the two faces of the same coin. Things are happening in presence when you try to measure, and things are happening when you don't measure. These are two different worlds in quantum realm. Now again, see, because we are discussing the time-dependent perturbation, the point is why time matters. Why time matters? Because you are inculcating the change of the disturbance. Your disturbance is changing, and that change can be measured in time, right? So time adds the flow and the evolution. You have evolution operators in quantum mechanics. You evolve your operators in the framework of time. When changes happen over time, the system evolves. Sometimes smoothly, sometimes dramatically. So dramatically here is directly telling us about the scattering, right? So when I say dramatic change, that's scattering. When I say that you have a smoothie kind of disturbance, then certainly I'm talking about the perturbation. And certainly, perturbation seems to be more fundamental. It seems to be more beautiful than that of scattering. So time lets us explore. Okay, you started somewhere, you ended somewhere. Not just what is, but how things become. Okay. So we have two frameworks, time dependent. Now how can I differentiate the two theories? In case of time independent, the disturbance that you're adding to a system is constant. It doesn't change. I apply the magnetic field. I'm applying a constant magnetic field. I apply the electric field. I apply the force. Anything that causes disturbance to my system has to be constant. So if it's constant, then it does not depend on time. Get me to the point? And when I add the change of my disturbance, even if that disturbance is very, very short, a small pulse, then certainly your system is going to evolve in the framework of time-dependent perturbation theory. So a pulse, a wave, or a flicker, this distinction changes everything about how the systems behave. It changes the course completely. What you understand in the framework of time independent changes totally when you discuss the same problem in the framework of time dependent disturbances. Now, this is how we approach the complex problems, because we cannot exactly solve the complex problems. Mathematically, we are weak in solving a three-body problem. Even for two-body problem, you use a lot of paper. And if you have to solve a three-body problem analytically, it will take 3-4 copies. For that, you need simulations, you need approximations to get some information about the system. So, we know the full picture of the lake which was not disturbed. We know the full picture of the haze in which the person was standing. We know the full picture of the tuning fork that was not doing anything. We know that mathematically. But what we are adding here is the disturbance, a short disturbance. So this approach helps us to navigate complexity by staying grounded in the simplicity. Now what is the simplicity here? Come on. The sleeping lake. The lake in the dawn of the day, in which you can see the reflections of the sky. That is the simplicity. That is your unperturbed Hamiltonian. Getting my point? Right. Again, time-dependent perturbation theory asks us, how does a quantum system respond to a changing external influence? And this would be a flash of light, as I said. I gave that an example. Can be that flash of light, a varying field, or any temporary disturbance that you can think of. It means the change is not violent or overwhelming. We are just nudging. We're just nudging the system, not smashing it apart. This keeps the original identity of the system mostly intact. A sleeping lake with the waves that you produce when you disturb it by a small pebble. You predict the possibilities. You're not certain about the results. You don't predict the certainties. You predict the possibilities. If nature would have been like certainties, people will not die. We will have no end. It will be completely possible to give you an infinite life. But the Creator is playing with possibilities, it's playing with probabilities. That's why we die, the things go off. So quantum mechanics never says what will happen, only what might happen. Suppose a person is there, has a disease. What science can tell about this disease? Suppose it's a very dangerous disease. It will give you the probabilities, but it will not be in a position to completely cure the person. Because his machines, his actions, they are all based on quantum mechanics. And quantum mechanics works on probabilities. There is a probability that this man will die. There is a 30% probability he will die. There is a 70% probability that the man will live. That's why in real world we have probabilities. So quantum mechanics is more fundamental than any of the sciences that we have around. It's more fundamental than biological sciences. It's more fundamental than chemical science. It's more fundamental than any science that's there in this planet. The energy levels, they dance when you exert that disturbance. Now see, imagine energy levels like a different floor. This is a floor 1, there's a floor 2. Okay? Now, to make a transition from floor 1 to floor 2, if you say Newton, what does that mean? I have a ball in this floor, this ball has to go to the floor 2. What does Newton mean? Come on, give the force to the ball, this much of force, the ball will go into the floor 2. That's Newton. But that's not if you have a quantum system. You have a quantum floor 1, you have a quantum floor 2. You have to give the right energy, you have to give the right disturbance at the right time. Only then you will have the probability that this ball will go into the floor number 2. For Newton, it's not possible. It's not a big deal. Okay? But for quantum framework, you need everything accurately, because there are a lot of things that are forbidden. Could you imagine for a ball in floor 1 that this ball will be forbidden if all the forces are available? Even if a giant is on this door, you will throw the giant, you will take the ball in your hand, you will face everything, and you will go to the floor number 2. But that's not the case here. What is important here is the jumps. But these jumps are dependent on timing. Appropriate strength. From Newton's point of view, you can throw your ball to the 10th floor, depending on the amount of energy that you are using on that ball. But here, you need the timing, you need the strength, appropriate, and the compatibility. why that violin was buzzing. Why? Why was that violin buzzing? Come on, can you answer that question? When I used the tuning fork. Because there was a match. You may call it an emotional match was there. And that match led the buzzing of that violin. If it would have mismatched with the violin, maybe the violin would not have responded. So these are the real world analogies. You can see them. A child on a swing being pushed at just the right rhythm. A violin string vibrating when another nearby note is played. A whisper that grows louder until it changes your mind. These are the examples. They talk about the timing. They talk about the harmony. And your system is transforming. This is what perturbation is. That's why when you deal with solving the problems, you see those symmetrical equations. You have sine thetas, you have cosine thetas, you have symmetries. You're always looking for these symmetries. Now, your disturbance can be sudden. If it is sudden, it is not perturbation. And it can be slow. When it is slow, it is perturbation. But when it is sudden, it's certainly scattering. It's certainly something that's happening violently in the system. These extra forces. What can be these extra forces? Light from a laser, a pulse. It can act as a perturbation. But it has to be a pulse. In case of non-degenerate perturbation theory, it was not a pulse. Keep that in mind. It was a constant disturbance. Its magnitude was same. That's why you have a time-independent perturbation theory. Getting my point? But here you have a pulse, a magnetic field, electric field, a vibration. They all influence the quantum systems. And these are all disturbances that are dependent on time. As I was saying, flow 1, flow 2. Okay? A quantum state can make a transition, like changing moods or identities. Now see, sometimes suppose I'm sitting here, I'm talking to you. My mood can change. Maybe I'm happy right now, I'll be sad. Maybe I'm less happy, I'll be more happy. What's happening in me? There are transitions. These are quantum mechanical transitions that are happening in my body, and they are making that sense to me. But it's not like that every time I laugh. It's not like that every time I cry. It's not like that every time I'm serious. But whatever am I am making transitions. And why I am making transitions? Because I'm influenced by the environment around me. The atoms of which I am made of, they are making transitions. Right now, I'm in a mood to give a class in this classroom. I will find a transition. I will leave the room. Getting my point? So these transitions are equally valid in our day-to-day lives, because they are all probable. I will stand up this boy in this room, and we will all go out of this room. Say, for example, what this boy will do. Do you know? But he has many possibilities. He can feel, I will sit for a while. He can have something in his mind. He will open the door, or he will see outside. Why he is doing that? Because the transitions are acting in his brain. There are atomic transitions that are happening in his brain, and that's leading us to have all these actions. Let's not go so deep. So this is the resonance that I was talking about. Resonance between the tuning fork and and the violin that you have. So resonance is like perfect alignment in timing. See, time makes beauty here. When an influence matches the system's natural tendencies, what's happening? It responds strongly. It responds strongly and efficiently. Resonance leads to the rapid and likely transitions. The violin was not responding, it was dead. I'm in the room, tuning fork, hitting it. A small vibration. The vibration matches with the vibration of the violin. It responds. There is a resonance. You understand the resonance? The frequency matching. When the frequency of the two things match, what happens? The amplitude is maximum. That's what resonance is. And that's what quantum probabilities are. These are the resonances in the background of time. So resonance leads to the rapid and likely transitions. As I said, all transitions are not possible, which is not the case of classical physics. In classical physics, all energies are possible. You cannot think, if I threw a ball, can you imagine that at any point this ball will have no energy? It has continuum of energies, right? But in quantum domain, what we have? We have discrete energies. We have possible transitions. We have forbidden transitions. Atoms absorbing light and becoming excited. Medical imaging, you can see my skin by perturbing my skin by an external force. It can be a magnetic field, like we have in MRI, right? It can be a CT scan where you use a radiation, make them interact. So, what we have, where quantum jumps, power, lifetime dependent effects are everywhere. You will see this. This is happening everywhere in the universe that we are studying. It's the core of everything that's happening around us. That's what's called as life. It has strong implications on the modern physics. In all frameworks, in all domains. It helps us understand how atoms emit light, how quantum computers process information, how particles behave in early universe. It's really foundational for the technology and the theory of life. So, this is the summary of the key ideas. I think I have taken care of all of these points. You can go through Feynman book to have more philosophical understanding on it. And these are some of the important books that you can use if you are very much interested in understanding the philosophy of the subject. And still, you see, there are questions. There are open questions. Don't you believe that if man would have answered to everything, man would have declared himself as a God? And it's the quantum mechanics that's giving us all of these probabilities and making people believe that there is someone who has created us. Now, it doesn't matter whether we are Muslims or Hindus or Christians. No, the point is there is a complete understanding that things are not in our hands. We are being governed. We are governed, whatever we are. So can we fully predict how a system will respond? What is the nature of influence itself? Is time a background stage? The time I was talking about. I choose this time on my copy. Does it actually exist there? I don't know. I'm not sure about that. But the time is something fundamental. But I understand the results. When I get the results, they dictate me, they tell me that, come on, there must be the time. Because the results that I'm obtaining, they are matching with the experiments. So with this, I think this is the end of this. So I hope I have tried to make an impression. I have tried to make you feel, make you realize what we are actually discussing. So with this, I would like to thank you all. So, bye.